Okay, this lesson will be on something that we call ice tables or equilibrium tables. I've heard them called both. I like ice tables because ice just sounds cooler. Ice tables are a way of organizing your information. It's all it really is. It's an organizational tool. I often have students who will ask me, Mr. P, do I have to use an ice table on this one? Or they'll come in and say, I couldn't do it. I did an ice table, but it didn't help me. You never have to do an ice table. It's just like it's just an advanced way of showing your work. If you're some sort of mathematical prodigy, if you're the kind of person who just sees numbers really well, you absolutely do not need to use an ice table, but it is extremely helpful for the rest of us mere mortals. What ice really stands for is just a table set up to keep track of what the initial conditions are in an equilibrium, what the change in those conditions or concentrations are, and then what the ending or equilibrium concentrations are. So the best way to do this is just to hop in to do an example. Let's look carefully at this problem and see what we can do. At 1,000 Kelvin, and the temperature is usually included just for completeness sake. Remember that the equilibrium constant does depend on temperature, so we may or may not need that number, but it's included for completeness. A quarter of a mole of sulfur dioxide and a fifth of a mole of oxygen react in a 10-liter vessel to form 0.162 moles of sulfur trioxide at equilibrium. What's the equilibrium constant? Okay, the first thing you need to know about ice tables is that they don't work well with moles. We'd like to have things in concentrations. Things just seem to go better. I've seen people do it with moles, and you can do it, but you have to be extremely careful. So let's change everything to concentrations first and just make a habit of that. So we have a 10-liter vessel. We're going to divide each of these moles by 10 liters in order to get them into a concentration, a molarity, and we get our three numbers changed into molarity. Now, I would say write the reaction. Do a good job, carefully balance it, make sure it's right. The question says sulfur dioxide and oxygen react to form sulfur trioxide. So when you draw an ice table, you write ice vertically over on the left side, and I like to put a line through the between the C and the E. That's where we're going to sum things up. And I also have had some students who will draw a line between the reactants and products, and I kind of like that too. It helps us to see things a little more clearly. Now, when we fill this thing in, you have to read the problem carefully. And this is the hardest part, is just to figure out where these numbers should go. It says that the quarter mole of sulfur dioxide and the fifth of a mole of oxygen are reacting in the 10-liter vessel. And so those are initial conditions. So we put them in the I row of our ice table. We're putting in a quarter of a mole of sulfur dioxide and a fifth of a mole of oxygen. There's no sulfur trioxide to start from what I can get out of this problem. It says after a while there's 0.162 moles of sulfur trioxide, and we've changed that into a molarity up here on the top. So at the end we end up with that much sulfur trioxide. So now we've got all of our information kind of plugged in here, and it allows us to kind of see the way to proceed forward. The C in an ice table stands for change. So if we started off at 0 sulfur trioxide and ended with this much, we must have gone up 0.0162 molar. Okay? Now, if the right side of this reaction is increasing, that means all of them, if there was more than one, they would all be increasing over on the right. That's the rules. If one of the products is increasing, they have to all be increasing. So we make them all at the same time. And that, furthermore, it means that the other side, the reactants, must be decreasing. So if this side of the line, of this side of the reaction is going up, then that side of the reaction, the left side, must be going down. Those must all be negative numbers. So, here's where we have to think about stoichiometry. Since there's 2 sulfur trioxides in the reaction and 2 sulfur dioxides, if this one is going up 0.0162, stoichiometry says there's a 2-to-2 ratio, a 1-to-1 ratio between these two. That means that this one would be going down that much. The sulfur dioxide would decrease the same amount that the sulfur trioxide would increase, because it takes 2 of the sulfur dioxides to make 2 sulfur trioxides. And then also, carrying on that same stoichiometric line of reasoning, this oxygen would be going down, and it would be going down half as much. So we take our 0.0162 and divide it by 2. The oxygen is going to decrease, but only by half as much, because oxygen's coefficient is a 1. And so if we take this now and we solve for what our ending concentrations would be, we have the information we need to find the equilibrium constant. The equilibrium constant, what I shift this up here to make some more room, is simply the sulfur trioxide squared over the sulfur dioxide squared times the oxygen. That's our equilibrium expression. if we plug in the numbers that we found here and calculate, we can say our equilibrium constant is 285 for this particular reaction. Let's do another one quick in order to just kind of drive this idea home. We've got this process where we make ammonia out of nitrogen and hydrogen. It's called the Habra process, one of the most industrially profitable reactions that are out there. And this equilibrium exists between these, the ammonia and the nitrogen and the hydrogen. Okay? So we balance our reaction and we fill in what we know from this question. You can probably pause the video and take time to read the question here. I'm moving quickly to get through it. But our beginning concentrations of nitrogen and hydrogen are calculated now, and we have got our ending concentration of hydrogen is given to us. We don't know anything about the ammonia other than we start with 0 of it. But based on what we have here, we can calculate that the hydrogen has been decreased by 0.151 moles per liter. And so if that has gone down 0.151, first of all, it means that the nitrogen is also going to be going down because they're on the same side of the arrow. It means that the ammonia is going to be going up because it's on the opposite side of the arrow. So, thinking stoichiometrically here, if this is a 3 and this is a 1, this would be 3 times as big as this. It takes 1 of these and 3 of those to make this reaction go. So these are going to go down 3 times as fast as this one is going to go down. And also, we can then carry it across and say, well, if this is a 1 and this is a 2 right here, that whatever this is going to go up because it's on the other side of the arrow, and it's going to be twice as much as this. So we fill in our numbers as we go across here and calculate our ending concentrations. We got them right there, and it asks us what is the equilibrium constant. So we plug in our numbers into our equilibrium constant expression, and we get that the equilibrium for this particular reaction at this temperature is 7.42. Now both of these examples have been examples where we were finding out what K was. We were solving for what KQ was on both of these things. Now, it doesn't have to be like that. We could solve for what an ending concentration would be. We could even solve for what a beginning concentration was. But this ICE table is a way for us to organize our thoughts so that we can see the way to proceed. It helps us to make sure that we are checking our work and that we're moving in the right direction. You might write one out and find out that it's not helping you at all. And that's fine. It means maybe there's a better way to do this. You may find that if you get good at this, you don't need them at all. But it's always something to think about doing. Stop and write an ICE table to see if that will help you.